If a polynomial with non-negative coefficients has only real zeros, then those coefficients satisfy two properties called log concavity and unimodality. So if we have a polynomial a0 plus a1x plus, let's say it has degree d, that has non-negative integer coefficients and only real zeros, then its coefficients are log concave. And by that I mean that ai squared is greater than or equal to ai minus 1 times ai plus 1 for I equals 1 to d minus 1. And this follows immediately from the Asen-Schoenberg-Whitney theorem. So we have that the determinant of the infinite Toeplitz matrix the 2 by 2 determinants are all non-negative. So that's that. Then the other property is called unimodality. So if this coefficient, if this polynomial has only real zeros, then the sequence a0 through ad is unimodal. That is, it has only one peak. The coefficients go up and then they come down again. So to see this, let's assume that the constant term and or the lowest coefficient and the highest coefficient are non-zero. So strictly greater than 0. If the constant term is 0, we can divide by x and get another polynomial where the constant term is not 0. Now if the sequence A0 through AD is not unimodal, then we've got at least two peaks, and we can find an index k such that AK is less than or equal to the two things around it. Actually, if they were equal on both sides, that wouldn't be a contradiction to unimodality. So let me say this. It's got to be strictly less than something on one side, and then less than or equal to what's on the other side. So it could happen with the strict inequality on the left or the strict inequality on the right. Now this pretty much shows that the middle one squared is not going to be greater than the product of the other two. Except if the middle one is 0, we'll have a problem. So if AK is greater than 0, then we have AK squared is less than AK minus 1 times AK plus 1 in both of these cases. So that means that the coefficients are not log concave, and therefore the polynomial does not have only real zeros. Alright, so now what if this coefficient is 0? Now if AK is 0, then these two inequalities become so well, let's see. The inequalities, I guess, would be fine if this is the only thing that's 0, but if we're allowing equality on one side, then the equalities could become AK minus 1 greater than 0 equal to 0, and 0 less than AK plus 1 equal to 0 on this side. And then 0 this gives 0 squared equals 0 times something else, which is not a problem because then they're equal. But actually there is a problem if AK is 0, it's not this immediate problem. So we have a sequence of a subsequence of zeros somewhere in that coefficient sequence of the polynomial. So 0 coefficients, a subsequence of coefficients equal to 0. Then in the tuplets matrix, we have something like AI, a bunch of zeros, AJ, and then AI here, and a bunch of zeros, and AJ there. And these two rows already give us a problem, because then we have the 2 by 2 submatrix. If we look at this column and that column, we have the 2 by 2 matrix 0, A1, AI below it, and then AJ and 0 below it. So I'm assuming AI and AJ are both positive. So the only zeros are the ones I've written in as 0. And we've got this 2 by 2 submatrix inside of a matrix which is supposed to be totally non-negative, but this says determinant equal to minus AI AJ. And thus, this polynomial does not have only real zeros. By the Asen-Schoenberg-Whitney theorem. So if you look at the PDF file that I posted of polynomials with real zeros, you'll see that the coefficients sort of go up nicely and come down. They make sort of curves that look a little bit like the normal distribution. So, as an example of these facts, we could look at a polynomial and ask, does 1 plus 2x plus 5x squared plus x cubed have only real zeros? The coefficients go up and come down again, so unimodality holds. But log concavity does not. So if we look at this coefficient, 2 squared is not bigger than 1 times 5. Two squared is 4, and 1 times 5 is 5. So no, the coefficients are not log concave. And then if we look at a polynomial like 1 plus 3x squared plus 3x to the 4th plus x to the 6th, we could ask, does that polynomial have only real zeros? And the answer is no, because, well, it looks like the coefficients are log concave, but this is actually 1 plus 0x plus 3x squared plus 0x cubed plus 3x to the 4th plus 0x to the 5th plus x to the 6th. So the coefficients are in fact not log concave. So we can use log concavity and unimodality to prove that a polynomial does not have only real zeros, but they're not sufficient conditions to prove that a polynomial does have only real zeros. Log concavity implies unimodality, so log concavity is not sufficient to prove that a polynomial has only real zeros. So for example, 1 plus 2x plus 3x squared plus 2x cubed plus x to the fourth is unimodal. 1, 2, 3, 2, 1 goes up once, comes down. 2 squared is bigger than 3 times 1. 3 squared is bigger than 2 times 2. 2 squared is bigger than 1 times 3. But this polynomial does not have only real zeros. This has at least one pair of imaginary zeros. And I can see that for other reasons, which I'm not going to explain right now. But just wanted to say that to show that this condition is not sufficient to prove that a polynomial has only real zeros. The end.